In the last video, we looked at vectors and how they affect our force equations. Now we're going to take a look at momentum and see how it's affected when we treat momentum as a vector quantity, which it is. Let's take a simple example, two carts on a frictionless track. And this will be cart 1, and this will be cart 2. And cart 1 has a mass of 1, and cart 2 has a mass of 2m, twice as much. Cart 1 is moving to the right with speed 2 v0. Cart 2 is moving to the left with speed v0. And we want to know what's going to happen when they collide together. So there's a momentum in cart 1, m times v, and there's a momentum in cart 2. And the magnitudes are the same. But we know that momentum's a vector quantity, and these point in opposite directions, so they cancel each other out. The system actually has zero momentum at this instant. And that means after these two carts collide, the system of these two carts also has to have zero momentum. A more formal approach is to assign a coordinate system and a positive direction. Let's call the right our positive x direction. Our momentum 1, if we write it as a vector, is going to have this magnitude in the positive x hat direction. And our cart 2 is going to have the same magnitude, but it's going to be in the negative x hat direction. Usually we don't write it like this. Usually we write it as negative 2m v0 in the x hat direction. The negative sign just indicates direction. This is a vector quantity. So we can add them up. The initial momentum is 0 because we add these two up and they cancel out. We get 0 initial momentum. So afterwards, we also have to have 0 momentum. This has to equal our final momentum. After these two carts collide, let's have them stick together. So it makes it a little easier. We have a mass of 3m and some final velocity we're trying to solve for. And we know that this has to equal 0. It has to equal our initial momentum. So we can divide by 3m, and we get the final velocity is 0, which we knew already. Let's make it a little more interesting. Let's have both of these carts going in the same direction. This time, cart 1 is doing the exact same thing, moving to the right with a speed of 2 v0. Cart 2 is also going to be moving to the right with a speed of v0. So cart 1 is catching up to cart 2, and it's going to crash into cart 2 and stick to it, and the two will move together. So cart 1 has some initial momentum, and it's to the right. Cart 2 has some initial momentum. It's also to the right. So both cars have the same momenta to the right. Now afterwards, they stick together. So our total mass here is going to be 3m. And we want to know what's the final velocity of the carts after they collide and stick together. So we say the final momentum is going to be the mass times the velocity. So initially, we had P1 initial plus P2 initial. And at the end, we just have them stuck together. And we get V final is 4/3 V initial in the x hat direction. Using unit vectors helps clear up any ambiguity in the direction. We can see that cart 1 slowed down. It was moving at 2 V naught. Now it's moving at 4/3 V naught. It slowed down a little bit. It received an impulse to the left, causing it to slow down when it collided with the other cart. Cart 2 was moving with speed V naught to the right, and after the collision it's moving faster. It's moving with a speed of 4/3 V naught to the right, because cart 1 gave it an impulse to the right, increasing its momentum. But because the total momentum of our system is conserved, the amount that one loses is the same as the amount of momentum the other one gains. So if the delta P for cart 1, it lost a certain amount of momentum, the delta P for cart 2, it has to gain the same amount of momentum to keep the total momentum of the system the same.